Dear students, in this video, we'll see what is small signal operation and why small signal operation is required. So that is very, very important. This is a very important concept which we are going to understand in this video. And we'll also be seeing the derivation of the transconductance, okay, which is GM. So this is very much required while understanding the concept of T model and pi model. See, whenever we take any transistor, we do two types of analysis. Okay, one is the DC analysis. What we do is one is DC analysis, and the other one is what we do is your AC analysis. Okay, AC analysis. Now, when I go with DC analysis, I am when I go with DC analysis, I am worried with finding the value of VC, IC, sorry, then VCE, okay, your VB, your VE, and you'll also have other currents like IE and IB. Finally, what is VC? So all these values we are able to, we will be calculating when we do DC analysis. So what are the biasing circuits which we derived, which we worked on in the previous videos and all? Those things what we did is all DC analysis. Okay. Now, one more thing which I need to tell you, in most of the books, what they actually, notation that they use for mentioning DC currents or, DC values or AC values, and also the mean, RMS values. So when you see anything with alphabet which is completely capital I, capital C, this is your DC collector current. So this would be DC collector current. So keep this in mind. I'm trying to say very important factor for you. Now, if you see a small I with small c, okay, this would be an AC collector current. AC collector current. If you see a small I with a capital C, then this is called as instantaneous collector current. Instantaneous collector current. Now your instantaneous collector current is actually, this instantaneous collector current is actually equal to the DC collector current added with an AC collector current. Okay, so DC collector current added with an AC collector current. So therefore, these notations are very important. Why I'm saying you, because further in my explanations I will be using such notations. I will not be telling you what is capital I, capital C, or what is small c, or what is small I and capital C. I will not be telling you what type of value is that. You should be able to, recall these things, whatever I'm saying you now. And if you go with IB, like base current or emitter current, it holds the same. Okay, you see capital I, capital E, that is emitter current, which is DC. Small I and small e, that is emitter current, which is AC. And small I with capital E, that is instantaneous emitter current. And summation of DC plus AC is what? Instantaneous. So keep that in mind. Okay, so I'll just erase this now. So keep that in mind. You will be remembering this thing what I told you just now. Now coming to AC analysis, let us start with that. Now before doing AC analysis, anyway, I want to tell you this. When I go with AC analysis, that is where you will come across with T model and pi model. Now with these two models, why do we go with these two models? These two models will allow me to derive the equation for voltage gain. This will give me voltage gain. This will try to give me the derivation for current gain. This will give me for input impedance, to measure input impedance. This will also give me a path for measuring the output impedance, and so on. Okay, so therefore, as I told you earlier, if I am not told, please listen. Any amplifier circuits that we design, we go in measuring four different things. Okay, we go with four different things. One is to amplify the voltage. One is to amplify voltage. The other one is to amplify the current. We are going to amplify the current. The third, what we do is measuring input and output impedance. Even fourth is also same. See, third and fourth is like somewhat like maybe input infinity, output zero, or input zero, output infinity. So these measurements we do. Anyway, all the amplifiers what we design is completely based on this. We design an amplifier which can amplify voltage. We design an amplifier which can amplify current. We design an amplifier which can give you, infinite input and infinite output impedances. We design an amplifier which can give you zero input impedance and zero output impedance, and so on. So therefore, whether a single amplifier will give you all these terms, no. It all depends on the way you design the amplifier to obtain these parameters. Okay, so fine. So now let me go with this P model, pi model, voltage amplifier, current amplifier, and all in the later stage. But first, the current understanding what we need to do is now is how a small signal when we apply the amplification will come into picture. Okay, what is the benefit of doing this small signal operation in any BJT transistors that you take? Okay, so now if you see the circuit, this is a DC base emitter voltage, and if you see this is the small VB. If you see, this is actually voltage which is AC voltage, base emitter AC voltage. And if you see this VB, I can easily say the first equation here is a small v with capital B, which says instantaneous base emitter voltage, which is equal to summation of these two voltages, what you see here, which is nothing but VBE, capital V, capital B, plus small v, small b. So this is DC and this is AC. Okay, so instantaneous equal DC plus AC, which I told you. Now the instantaneous collector current of BJ summation of the DC current added with an AC current. Now we do have a collector current equation, in terms of saturation current multiplied by E power base emitter voltage divided by the threshold voltage, the thermal voltage. Okay. This is the normal equation for IC. What we see, IC will always be increasing in terms of base emitter voltage, which is E power exponential increment of base emitter voltage. Okay, so therefore, this is the proper equation for IC that we normally write. So when I write the same equation in terms of instantaneous current IC, I can say that is equal to IS into E power the instantaneous VBE divided by the thermal voltage VT. Okay, this is now expanded. I can expand this. I can write the instantaneous base emitter voltage as summation of DC voltage plus AC voltage divided by VT. Right? Now this can be separated as E power VBE by VT into E power small VBE by VT. Okay, so because e power a plus b can be written as e power a into e power b. Okay, so now if I if I take this equation IC equals IC plus IT, so I can say that this IS into e power VB by VT is your capital means the DC current, the capital DC current IC into e power VB, small VB by VT. Okay, so if I go further and if I write your instantaneous collector current equals your DC current IC multiplied by e power small VB by VD. So now if you see this instantaneous current, your instantaneous collector current is completely dependent on the DC current IC and a small signal voltage which is applied, which is small VB. Okay, so this is how a small signal operation, can increase the collector current, instantaneous collector current in terms of exponential. Okay, a small signal VB can vary the collector current IC exponentially. That is the reason in BJT, whenever we are using BJT for an amplifier, we normally give voltage, input voltage in millivolts. And we are going to get minimum more than 10 times the expansion that we get in terms of output when we measure. So if I give 100 millivolts, the output can reach till 3 volts, 4 volts and all. Okay, so therefore, that is the reason a small signal can vary the collector current in a huge manner. Okay. Now for this, if I apply the Taylor series, okay, if I apply the Taylor series for this, what is the Taylor series? I'll just write the Taylor series here. In mathematics, we have something called as Taylor series. In mathematics, we have something called as Taylor series. Taylor series. So what is the Taylor series says? If I say e power a, okay, if I say e power a, this e power a can be expanded as 1 plus, e power a can be expanded as e power a can be expanded as 1 plus a plus a square by 2 factorial plus a cube by 3 factorial plus so on. So this is the Taylor series which we had in mathematics. If I substitute the Taylor series for this, see this is in terms of e power a, right? If I say that, I will be able to say that e power small VB by VT can be expanded as 1 plus small VB by VT plus small VBE by VT the whole square by 2 factorial plus so on. Okay. I can expand this e power VB by VT in this term. And I told you that VB is small VB is very small because it is a small signal operation which we say. And you have VT which is in the denominator which is equal to 25 millivolts. And this VT is very high compared to VB. So therefore, if you take VBA by VT the whole square, VBA by VT the whole cube and all, these terms will be approximately, this entire term after this will be equal to 0, approximately 0, because you are going to square the denominator term. So 25 milli square. So denominator is getting squared, denominator is getting cube. So therefore, anything divided by the maximum value square or maximum value cube when it is there in the denominator, the value of that will be approximately equal to 0. For example, if I say 1 by 2 square, like 1 by 2, then I will take 1 by 2 the whole square. Okay, and that will be equal to 1 by 4. Now if I say 1 by 2 the whole cube, this will be equal to 1 by 8. Now, if you see, this is 0.5, whereas this is 0.25, this is 0.125. Gradually, you are able to see the value is getting lesser and lesser and lesser. So therefore, this entire term will be equal to approximately becomes very less, so approximately 0. So finally, I can say that e power VBE by VT, e power small VBE by Vt is equal to 1 plus small Vbe by Vt. If I substitute this in this term, in this instantaneous current term, what will I get here is I instantaneous collector current equals DC current IC multiplied by 1 plus 1 plus VBE by small VBE by Vt. Small VB by VT. Okay. So therefore, your IC, instantaneous current IC is now equal to instantaneous current IC is now equal to IC plus IC plus IC plus small VBE into IC by Vt. I've just taken, if you take IC and multiply it to this term, you can just write in this way, right? IC by Vt, Vb into IC by Vt. Okay. So if I further go with this, expansion, your small IC, small IC is nothing but this term. This is the small IC term, right? Your small IC is what, because earlier I told you that instantaneous current equals summation of DC current and AC current. Summation of DC current and AC current. You have a DC current here, and this is the term which will now become AC current. So therefore, I will say finally the AC current IC equals the AC current small IC equals small VBE multiplied by IC by VT. Okay, small IC equals VBE multiplied by IC by VT. Therefore, as I told you, we are deriving the equation for GM. Therefore, your GM is actually equal to, your GM is actually equal to, you all know that conductance. Conductance is the reciprocal of resistance. According to the Ohm's law, we know that R equals V by I, and the conductance is I by V. Okay, so this is the Ohm's law which we normally know. So therefore, the conductance in this equation Vm equals IC by Vt. So this is the formula for the conductance in terms of, in terms of BJT. Therefore, your small IC collector current, AC collector current equals VB into GM. Very, very important term which I am telling you. The AC current IC equals VB into GM. Another factor which you need to see here is, as IC is very high, IC will be very high. Means collector current increases in amplifier circuit, so when BJT is considered, due to which the transconductance of BJT is very small value, very small, is very low what we use. Okay, it is very low because IC is very high. Definitely, the transconductance of the transconductance of BJT is very transconductance of BJT is very high because GM is directly proportional to uh, transconductance of BJT is very high, very high. So, because GM is directly proportional to IC, transconductance is very high because GM is proportional to IC. Therefore, input impedance of BJT is normally 1 over GM. And GM is very high, input impedance of BJT is very low, very low. Okay, so normally that is the we normally this is the drawback of BJT which you can consider because the transconductance of BJT is very high, but unfortunately the input impedance becomes very low. Okay, because of the transconductance being very high. So therefore, if you take the MOSFET. Later we'll discuss in module 2, we'll discuss MOSFET. So in MOSFETs, you see the transconductance will be very low, where input impedance will be very high. That condition we'll see later. Okay. So I hope now in this video you came to know about the transconductance and its formula. And we also know that we also came to know that finally the AC current IC is equal to the product of the base emitter AC voltage multiplied by the transconductance. Thank you. We have derived the equation for small IC. Now what we do is we will try to derive the equation for the base current IB and the base resistance or the input resistance at the base, which is normally called as R pi. Okay. Now this R pi is the resistance which is very much important when we come across with the pi model of the BJT transistor. Okay. So similarly, we will also try to see the current IE, small IE, okay, which is emitter current. We will also be deriving the resistance at the emitter, which is called as small RE. Now that RE, what we derive later, is very much important when we come across with T model of BJT transistor. Okay, now let us continue in discussing with finding the IB equation, small IB equation. Now I can say small I capital B, which is instantaneous base current, which would be equal to summation of the DC base current with summation of the AC base current. So the instantaneous base current can be equal to the DC base current added with the AC base current. Now this instantaneous base current can be written as IC, which is I capital C by B beta. So this instantaneous base current can be written as the instantaneous collector current divided by beta, because earlier we know that IC equals beta times IB we used to see, right? If you remember that in the previous videos. So I can also say that IB equals IC by beta. So this term we know it, right? So that is what the term which is replicated here. I can say the instantaneous base current is equal to the instantaneous collector current divided by beta. So this can be written as, we know that the instantaneous current was equal to, 1 over beta into, we knew earlier that the instantaneous collector current was the DC collector current added with the AC collector current was IC into small VB by VT. This we derived earlier, right? While deriving for IC, for GM, while deriving for the transconductance, we saw this equation. Now, if I expand this, I'll be able to see that this is equal to IC by beta added with IC by beta IC by beta into VBE by VT. VBE by VT. Now, if you see this, I can easily say that this term is the capital base current, which is nothing but DC base current, added with the AC base current. Therefore, I can say that the AC base current IB equals IC by beta into small VB by VT. I can also say that we know that earlier IC by Vt was equal to the transconductance Gm, right? So IC by Vt equals the transconductance Gm. So this, if I write Vb by beta multiplied by IC by Vt. So therefore, this will be now equal to VBE. This will be now equal to VBE by beta into Gm. VB by beta into Gm. So I can say now that your beta by Gm. Now this is your small IC, right? This is for small IB. So if I take beta by Gm, beta this side, Gm this side, I can easily write this ratio as beta by Gm equals small VB by small IB. Small VB by small IB. This small VB by IB, you know, V by I is, the resistance R. But here, the base emitter, AC base emitter voltage divided by AC base current is actually equal to the input resistance at the base. Is actually equal to the input resistance at the base. Okay, so this is your R pi. This is your R pi. Okay, so I think you came to know what is R pi. Now, if you see that beta by Gm equals VB by IB, R pi can also be equal to beta by Gm. Beta by Gm. So these are the two values for R pi. So we got the value of IB. Now we also got the value of IB, which is VB by beta by Gm. We also got the value for R pi, which is VB by IB. We also got the value for R pi, which is equal to beta by Gm. Okay, and we know that Gm is equal to IC by VT. So hope you got the derivation now to derive what is base current and also to derive what is the input resistance at the base. Okay. Now we'll go with the next derivation, which is the emitter current IE and the input resistance at the emitter RE. Okay. The emitter current IE and the input resistance at the emitter resistance RE. Similarly, how we wrote the equation for IB, similarly we'll write the equation for IE here. So I instantaneous emitter current is equal to instantaneous collector current divided by alpha. Okay, this we have learned, in the basic electronics. You might have learned this, where the capital current, the DC current IE is equal to the AC current IC, DC current IC divided by alpha, right? So now, if I elaborate this instantaneous collector current, I can say IC plus small IC divided by alpha, which is DC plus AC. So if I expand this, I'll be able to see that it is IC by alpha plus small IC by alpha. Now I can say the small IC we all know, which is capital IC divided by V2 into VB. So if I substitute that, so therefore this is your DC current IA and this will be my AC current IE. Okay, so I can say my AC current IE equals your AC current IC by alpha. Okay, this is small c. So AC current IC is nothing but capital IC into small VB by VT, which we saw earlier, and this is multiplied by 1 over alpha. Okay, so I can write this as VBE by alpha into IC by VT, and this can be written as VB by small VB by alpha into GM, and this is the equation for the AC emitter current I. This is the equation for the AC emitter current I. Now if I take the ratio now, what I'll do is I'll try to write alpha by GM, okay, alpha by GM equals small VB by small I, small VB by small I, right? So alpha by GM equals small VB by IE. So therefore, I can say that this small VB by IE, this small VB by IE is nothing but RE. Small VB by IE is nothing but RE. And I can also say that RE equals alpha by GM. Now this is the input resistance at the emitter, which is RE. Okay, so this is the input resistance at the emitter, which is RE. Okay, and you also got RE, which is VB by IE, and we got IE equals VB by alpha into GM, and I can also say GM equals IC by VT. Okay, I hope I hope you got how to derive the equation for the collector current. Initially we did that, then we derived the equation for base current, then we derived the equation for emitter current, we derived the equation for input resistance at the base, which is R pi, we derived the equation for the input resistance at the emitter, which is RE. What I'll do is, now what we do is, we'll try to find out the relationship between RE and R pi. Okay, so that we are going to do it now. We'll find out the relationship between RE and R pi. Let us see the relationship between RE and R pi. Okay, so for that we need to make a note of the equations which we derived earlier. So we derived for RE, which was equal to VB by small I, right? We also derived RE, which was equal to alpha by GM. Similarly, we derived for R pi, which was equal to VB by small ib, and we also derived the equation for R pi, which was equal to beta by GM. Now, if I take VBE here, only VBE, I can write this as RE into IE. This side, if I take VBE, I can write this as R pi into IB. Now, if I equate both, because both LHS are equal, therefore I can easily say that IE RE is equal to IB R pi. IERE equals IB into R pi. Now what I'll do is I'll take the ratio, or I'll keep R pi as it is, and I'll write R pi equals IE into RE divided by IB, I small. If I write IB in terms of IE, I can say my IE equals, sorry, not I will write in terms of IE. Yeah. If I say, IE equals, we discussed earlier, IE can be written as 1 plus beta times IB, 1 plus beta times IB, right? In DC biasing circuits, when we discussed, I wrote IE equals 1 plus beta times IB, if you remember. So similarly here, the AC current will hold the same equation. So here, what I do is I'll replace IE with 1 plus beta times IB divided by IB into RE. So if you see here, 1 plus beta, sorry, not 1 plus beta, IB and IB gets cancelled. IB and IB gets cancelled. You are left out with 1 plus beta into RE. Therefore, finally, my equation would be R pi is equal to 1 plus beta times RE. R pi equals 1 plus beta times RE. We can say 1 plus beta is approximately equal to beta. I told you long back that beta is very much greater compared to 1. So therefore, if beta is very much greater than 1, I can easily say that 1 plus beta is very greater than 1. 1 plus beta can be approximately equal to beta. Therefore, you see that R pi will be approximately equal to beta times RE. Now, these two equations is what the relationship between R pi and RE that you need to derive. Okay, so this gives the relationship between the base input resistance at the base and input resistance at the emitter. Okay, so with this, I think the students will have got how to derive the equation for small IC, which is AC current, collector current, AC base current, and AC emitter current. Meanwhile, also the input resistance at the base and input resistance at the emitter, which is R pi and RE. And also, I think students got how to derive the relationship between the R pi and RE. Okay, thank you.